Now, I was looking for a good sort of proof for you to show you how the derivative of e to the x works. It works differently than like x squared and x cubed and things. It doesn't work the same as a polynomial. It's got its own rule. I couldn't really find a very good proof, or at least not one that was good for us to feel good about. So I decided I would just do a little demonstration. Okay. So here's what I'm going to do. I'm going to say, hey Desmos, graph me a function. F of x equals x squared. Okay. And then I'm going to say, hey Desmos, graph me another function. But one of the things that Desmos can do is it can figure out and graph the derivative of a function. So we know, hopefully, we know that if f of x is x squared, then f prime would be 2x, right? Right? And so if I went down here, y equals 2x, I could just tell it to graph 2x and it would do that. But watch this. I'm going to tell it, hey, for g, graph, where are you? I need my functions. Hello, Desmos. I would like you to graph the derivative of the f of x function. And what you may or may not realize is it's graphing 2x because 2x is the derivative. So I don't have to have this here. I'm going to take that off. For x squared, the derivative is 2x, and Desmos has the capability. It can't show us the derivative in variable form, but it can graph a picture and show us visually, hey, if you're looking at f of x, a picture of its derivative will look like this. And we happen to know that that particular graph is 2x because we have other ways to do that. Right? Similarly, if this were x cubed, all right, it's graphing the derivative, it's graphing 3x squared. Okay. Same kind of thing. We know that if we're looking at x cubed, and we were going to talk about x cubed's derivative, the derivative of f of x, if f of x is x cubed, the derivative of f of x is be gx, and which is 3x squared, which is what that guy is. Okay. So, why do I care about that? Well, because I want to show you this. I'm going to put e to the x in for my function, and this is going to graph its derivative. Okay? We've already established it'll do that. We've proven it with a couple examples. We could do more. So here's e to the x. Oops. That was kind of anticlimactic because I typed it too. Here's e to the x. And its derivative. Now, if you notice, when I take the red function away, the blue function is there right underneath it. The blue function is the derivative. The red function is the original function. And so what this is just a demonstration of, it doesn't prove it, but it's a nice visual of exactly what I'm going to tell you, that when y is equal to e to the x, that y prime, its derivative, is also equal to e to the x. E to the x is its own derivative. It's one of two functions that does that. There's only one other function that if we looked at the function and we looked at its derivative, they would be identical. And that's actually kind of a really boring function. It's the function y equals 0. The derivative of 0 is just 0. The derivative of y equals 0 is y prime equals 0. The derivative of that is y prime equals 0. So y equals 0 has its own derivative, is equal to its own derivative. But e to the x is also equal to its own derivative. That means if I look at the slopes along the e to the x curve, the pattern of those slopes is an exponential growth. Okay? An exponential growth function has slopes that grow exponentially. If we wanted to do more of these, I said, hey, what's y double prime? It'd be e to the x. What's y triple prime? It'd be e to the x. Or like Mr. McCorkle, my high school calculus teacher, said, it's elephants. It's nothing but elephants all the way down. I don't know why he decided it was elephants. He just, because I to the E, I don't know. It was just one of the dumb things he said. So, which I always still remember all the dumb things. I love Mr. McCorkle. So, e to the x, elephants all the way down. I wonder if he's still alive. He should be. E to the x, elephants all the way down. The derivative of e to the x is e to the x. The derivative of that is e to the x. The derivative of that is e to the x. It's nothing but elephants all the way down. So, very different initially from a polynomial. Okay. X squared, derivative, 2x. We change things. E to the x, derivative, e to the x. Okay. Now let's look at other combinations. Because you know, you're like, well, that can't, I mean, our functions are not going to be just e to the x. We're going to have like constants and other things and numbers up with the x and other pieces. So let's look at what happens when we start putting additional stuff. Let's say I have 5 times e to the x. And I want to write the derivative right? So if I make this 5e to the x, well, all that does is move the graph up 5, and oh, okay, it looks like multiplying by a constant doesn't do anything exciting to the derivative. So not only is the derivative of e to the x, the derivative of a times e to the x is a times e to the x. An additional little constant factor doesn't change anything. Very boring. Okay. Now you might think, well, you know, is it ever going to be anything different? Is it possible to ever? And you might, you know, kind of like, it's got to be. There's got to be some time it's different. Let's talk about that guy. E to the 3x. His derivative is going to be a little different. Okay? His derivative is going to be a little different. So let's see. If I do e to the 3x, oops, I meant to, let's zoom in a little bit on that. Okay. So e to the 3x's derivative, the blue guy is the derivative, looks still like an e. It's got basically the same sort of shape, but on the original function, it goes through 0, 1. On the new function, it goes through 0, 3. I can't do very much else with points, but if I could, yes, it gets a little messy. Oh, I know. Oh, I can't do that without showing you what it is. Okay, so clearly it's something different. And the y is a kind of a key for that. Sorry. On the derivative, my y is 3 times as big. That's exactly what happened here. When I have e to the 3x, my derivative is e to the 3x. So that part still is the same, but then times 3. Now, if you had to guess, where do you think that 3 came from? Because of the 3x? Yeah, that's exactly where it comes from. This essentially is kind of like the chain rule kind of idea, but for exponentials. So the chain rule for exponential says, all right, if we've got, whoops, instead of just e to the x, e to a function of x, so like e to the gx, that my derivative is going to still have the original function in it, e to the gx, but I'm going to multiply by the derivative of whatever g is, so g prime. And no matter how complicated that g is, that's how this is going to happen. If I have e to any function of x, the derivative will be e to that function of x still. So notice that's the part that's still the same. The original function is still in the derivative. But when this is a function of x, you have to also multiply by the derivative of what's up there. Okay. You can kind of think about that all the time. If that's just x, this would just be a 1, and it just wouldn't change anything. If this is anything else, you know, any other function of x, you're going to additionally multiply by the derivative of it. So that means, like, for example, if I had, let's say we had e to the 5x plus 2, which we could. And we can get all kinds of different combinations of models. My derivative would be e to the 5x plus 2 times, and then I would look at this and go, oh, derivative of 5x plus 2, I need an extra 5. So times another 5. What you'll see me do is I will write my answers like that, and then I might rearrange it and clean, because I consider that a little bit of a cleaner answer, just to kind of put that extra constant out in the front. But I'm going to typically show you this because I really want you to see, oh, look, what was in the original function is still there. It's just got this little extra part. Okay. Now, the other function rules, or excuse me, the other derivative rules that we've learned are still going to be in effect. So if I happen to have a sum or difference of two functions, when I want to take the derivative of that, I'm going to think about each piece kind of as its own entity. That's what we always do when we have a plus or a minus between functions. We essentially treat each function separately. Products and quotients we got to be a little bit more fun with, but when it's a sum or a difference between functions, and that's what all basically polynomials are, just combinations of sums and differences of functions, we're going to treat each function separately. So the way we take the derivative of x squared is, using our typical power rule, But the way we take the derivative of 4e to the 2x would be using our exponential rule. So let's see. If you haven't written an answer for this yet, give it a shot. What do you think we're going to need? And then I'll write it down. 4e to the 2x plus x squared. It's a sum, so they're separate. What would my derivative be? The good news is in applied, we don't have to do a lot of cleanup, fancy algebra necessarily, unless we're going to do some things with these derivatives, which we might do a little bit, but we're going to use our technology to help us a lot. So I'm perfectly fine with leaving your derivative in this format. 4e to the 2x's derivative. Notice that there's 4e to the 2x showing up times 2. 2 because that's the derivative of 2x. That's the chain rule part of exponential rule derivatives. And then x squared, well, he's just a polynomial term, so we do power rule for him. Derivative of x squared is 2x. And so that's a good answer. Or, you know, if you want to do something like this, you can. If we wanted to write that as factors, we could, and we might do that if we were thinking about trying to get critical numbers, which is definitely a lot harder when we're dealing with exponential functions. All the things we do with derivatives, all the things we've learned about things we can do with derivatives, we can do with exponential functions. They're just, some of them are a little tougher because of the nature of the functions, a little harder to work with. But all we're focusing on today is really kind of the mechanics. Here is how we do these derivatives. All right. Questions? Okay. So let's do just a couple more practice just to make sure you've got the basics. So try these. Let's do this. So basically find me f prime of x. So number 1, f of x is 7, oops, oh no, we'll leave it. How about 7x cubed plus 5e to the 4x, there we go. And number 2 is going to be 10e to the x squared plus 2x. That's fun. That's crazy. Number 3 make this one 10 minus. Okay. I must have a thing for tens today. All right, let's write the derivative of each of these. Sort of different variations of difficulty, different combinations of things. You've got a little polynomial with a polynomial piece and an exponential piece in number 1. Number 2, you've got an exponential, just exponential number 2, but it's got a polynomial exponent, so a derivative is going to look ugly. And then number 3, you've got a difference. One of those is a constant, and you've got that negative x power, which is a little extra fun. Ooh, let me see something. Sorry, we've had a runaway what do I want to say? AirPod. I was going to say iPod. AirPod. Runaway AirPod. And we found one of them. If you see another AirPod laying around on the floor, it's kind of over there, Owen, by where you are. That he said he dropped his case and he wasn't sure. If you see another one floating around down there.
Do the ring thing. Okay.
Oh, did you find it? Is it an AirPod? It's an AirPod. Whose is it? Jake Gruber's? Yeah. Okay, yeah, because that's he just messaged me. Okay. Yeah, he said that's where he sits. And this is the other one we found. Here, do you want him? If I tell you, I'm going to tell him you have him, though, so if you don't give him back to him, he's going to get you. Okay. Here, I'll just message him. You message him, or I'll message him. Okay, here we go. Hi, Jake. We just found it in fourth period. We're not focused. There we go. Heroes. We're heroes today. Here, I'll do it here on my computer. It'll be easier. We'll leave out of there. Oh, now that's all recorded too. Fun. That's the fun part of recording things. Takes a village. All right. There we go. All right. So let's see what you did with these guys. Okay. One thing to remember is you're always, when you have an exponential piece, you're always going to have that exponential piece in your derivative. So when I build this derivative for number 1, this part is going to be there. All right. Times another 4. Oops, that's a weird looking 4. Okay. Then this guy, though, he's a polynomial, so I got to follow polynomial rules. Okay. So that's one version of the derivative for number 1. If you want to make that back piece a 20 times e to the 4x, that's totally fine. Okay. Like I said, that's not my first thing. I tend to write them this way initially for students so that you can see then where things came from, and then at least in applied, and then a cleaned up version, 20 e to the 4x. Okay. So either one of these is good. Number 2, yeah, your exponent on your e can be any function. You know, it's kind of like, you're like, well, why would you want to do that? Well, because we're kind of being theoretical right now. So we can do whatever we want. We can kind of make any kind of Frankenstein crazy function we want. It doesn't mean that it's actually good for anything, but when we're doing theoretical math, it doesn't have to be good for anything. We can just do it for fun. So, I can say, well, what if I wanted this as my exponent, and then I wanted to talk about its derivative? Well, I'm gonna have the exact same stuff all there times, and I need some parentheses for the second part because it's not just a single piece, times 2x plus 2. You might want to throw some parentheses around that too as well. Just kind of helps, but you don't necessarily need it. You definitely need to have 2x plus 2 in parentheses because you have to have this whole e guy times this. Okay. Positives and negatives can always throw us off. Sometimes constants do as well. Remember, a derivative of just a constant is 0 minus 8e to the negative x times negative 1. I'm going to put some parentheses around that just so it doesn't look like a subtraction. This I would most likely clean up. So positive 8e to the negative x is another version of that answer. Okay. What's in the exponent on that e can be anything, a single variable, a function of a variable. It could be a trig function. It could be anything. We don't necessarily have to have, right now, have a lot of meaning for this. Now, obviously, certain models that we use, we're not going to see as much variation. Like, it would take a little bit more work to develop a model that might create something like this as its model. Our exponential function models that we might create through our calculators are not going to be as sophisticated. They're going to be kind of all the same, just kind of like how all our quadratics and cubics are kind of all the same. So we won't be doing too many fancy things when we're doing our applications. But, you know, if I just want to throw some crazy combinations together and say, hey, show me a derivative, I can do that. I also, we have 2 more problems to do, can ask you to go back and use rules that we haven't seen for a while, namely product rule and quotient rule. Now, back when I taught you product rule, I did say, right now, you don't really see why we need it. But later on, when we start mixing combinations of functions together, potentially in products, and it's not something you can simplify first and just make one big polynomial, the only way to take the derivative of something like this is to use the product rule. We need the product rule to take this derivative because what we have here is literally the product of 2 functions, and they're 2 different types of functions. It's not 2 polynomials that you can just like FOIL together and make one big polynomial. It's a polynomial piece and an exponential piece. All right, so if you remember product rule, we would take g times f prime and we would add on f plus g prime. So we would take each function separately and we would take the derivative of each function and we would put them together in little combinations. And so my suggestion when we did product rule problems was to do a little side work and identify, okay, here's f and here's g. And then f prime, well, f is a polynomial piece, so f prime I'm going to think power rule. G prime is an exponential function, so we're going to use exponential function and rule and the chain rule of exponentials, so e to the 4x times 4 for g prime. So when I ultimately put this derivative together, it's going to look pretty messy. There's my g and my f prime. Here's my f. And there's my g prime. Lots of pieces. Now, what's the difference sometimes between what we do and what I might do in AB? In AB, we would do more with that. We would want to clean that up and factor it, and there would be a lot more, there'd be more algebra we'd have to do because we'd just be looking for mathematical skills that we can do. We don't need to do that. I mean, you can use that derivative exactly the way it looks. It doesn't have to be prettier. It doesn't have to be factored. It makes certain algebra things, if we wanted to do certain algebra things without tools, easier. And in AB, we do more without tools, but we're applying, right? We're always dealing with applying. So if we can work with it in this form, we're gonna. So they don't know what the derivative of e to the x is yet. So if you want to taunt them, you can. Because they haven't done that yet. They've done some integrals already. You guys are just in different places, doing things in different orders. So they're not going to be able to help you with e stuff, but maybe later on you can help them because they'll do that in the next unit. Product rule, you should both have those. So knowing how to take the derivative of e to the 4x, that's going to be you. Knowing how to pull product rule together, everybody should be able to do that. One function times the derivative of the other plus the reverse. Yes.
So when we get the h to 1x back there, whenever like that, we'll never need to like simplify that, right? Like,
I don't need you to simplify that. No,
Okay.
we do not need to simplify that. If, you know, there are ways you could factor a 2 and an x and an e to the 4x out of that, and you could write that if you wanted to. Pretty sure that would be 1, and that would be, this is one way you could rewrite that, and there would be a reason to do that depending on what other things we might want to do with this function without technology. They both have an e to the 4x as a common factor. They both have a 2 because there's a 4 here and a 2 here. They both have an x because there's an x and an x squared. So all of this can factor out, leaves me with 1, but I don't need you to be able to do that in this course. Okay? This is a perfectly acceptable answer that shows me everything I need to know, that A, you know product rule, and B, you know the pieces, how to do the e to the 4x derivative and the x squared. Last thing on the table for today, the other favorite rule, just to remind us, quotient rule. This one we kind of already always had to do. There wasn't a way to kind of get away from doing the quotient rule. G f prime minus f g prime over g squared. Just a reminder. So if I gave you 2x plus 3 over e to the x, take a minute and, using the quotient rule, write me a derivative. 2x plus 3 over e to the x, what would my derivative be? Okay. All right, so a little side work. Remember, F is always your numerator guy. So F prime would be 2. G is your denominator. And he's an elephant. So his derivative is just e to the x. The elephant's all the way down. I'm going to text my best friend from high school and I'm going to say, elephant's all the way down, and see what she says. She'll know exactly what I'm talking about. All right, so here we go. E to the x times 2 minus 2x plus 3 times e to the x, all divided by e to the x quantity squared. That's the kind of derivative that makes you just kind of feel like you're like, it's like e's everywhere and it looks scary. I mean, if somebody walked in here and looked at that board right now, they would probably like pee their pants. They're like, look, this is applied. They're like, oh, I'm never taking that. But it's not really that hard. It's not if you know the basics. It's just like anything. If you can't come into this for nothing, but if you know, since we know how to do the derivative of that, and we learned how to do the derivative of that, we can follow the formula and we can put this together. It's not pretty, but it's correct. If we wanted to try to do some stuff with it, we could distribute, we could simplify. This actually simplifies really nicely. We don't have to do that. I'm perfectly okay with that as an answer. If you want to do some alternate, some cleanup things to it, that's fine. Just be careful, and maybe, you and I might talk about that if you want to do some distributing or other things. Putting this 2 in front of the x is probably, one of the things I would do, just because I don't like that, but that's just me. Awesome. Okay, so you got to practice it. Just like anything, you got to practice it or you're not going to be able to do it on your own. So if we go to our Schoology group, there's just a little PP set of problems. Move them. They're all the way at the bottom though, because I copied them and then I did. So here they are. Move them to the top. So it's just a PDF of 8 problems. That's why I didn't copy it, because it's like you can just look at the problems and copy them down yourselves. It's not a long thing. There are 8 problems. You're going to find the derivative. They all involve e. Actually, on number 8, it says find the second derivative. I just posted the PDF so you can get the problems from it. You're going to do this on a separate sheet of paper. You're going to have this for me when you come to class on Tuesday morning. Okay? I'm gonna do this real quick so that if you prefer to copy them down right now, we are a little tighter on the time. You can do them. It's up to you. I'll zoom out a little bit. We are going to get our bell here in a few minutes, but if you want to do them right now, throw them in your binder. They'll be there. Have that. And so I